Welcome to The Explainer. Today, we're diving into the physical devices that hold our entire digital world. We're going to break down everything from the mechanics of old-school spinning disks to the silent speed of modern solid-state electronics, and really demystify the tech that underpins, well, everything we do. It's kind of wild when you stop and think about it. Every photo you've ever taken, every important document for work, your entire digital life, it all lives, physically, as information on a piece of hardware. And understanding how that hardware actually works, well, it has some major real-world implications, not just for speed, but for the safety of your data. So let's get into it, starting with a quick trip back in time to see where this all came from. The journey to store data has been a long one. Early computers back in the 60s and 70s used these incredibly tangible methods, literally punching holes in paper tape to represent data. From there, the big evolution was the move from the physical to the magnetic. So first came magnetic tape, which was a huge step up, but it had this one major flaw. If you wanted data at the end of the tape, you had to physically wind through the entire thing, just like an old cassette. And that's where magnetic disks came in. By arranging the magnetic surface in a circle, a read head could jump right to the data it needed, way faster. The whole evolution was about one thing: cutting down the time it takes to find what you're looking for. But that rotating surface, which became the basis for the hard disk drive, or HDD, well, it introduced its own set of problems. It was an absolute marvel of mechanical engineering, for sure, but at the end of the day, it was still fundamentally mechanical. Every single time you open a file, this intricate little physical dance takes place. An arm has to swing a tiny head to the exact right track on a platter that's spinning thousands of times a minute. Then it has to wait for that platter to spin around to the precise spot where your data starts. All of this takes a measurable amount of time, which, in the world of computing, is an absolute eternity. So get this. Before a single byte of your file is even read, you're already waiting. You're waiting for the arm to move, and you're waiting for the disk to spin. These two delays, seek time and rotational latency, are the fundamental bottlenecks of every single hard drive. And this really puts that delay into perspective. Even a super high-end server-grade drive spinning at an insane 15,000 RPM still has a 4-millisecond delay just waiting for the disk to spin. Now, when a computer's processor is doing things in nanoseconds, a millisecond is forever. It's a huge delay. And you know what? It can actually get even worse. As you use your computer, saving and deleting files, the different pieces that make up one single file can get scattered all over the physical disk. This is called fragmentation. It's like telling a warehouse worker to grab 5 items, but instead of being neatly on one shelf, they're in 5 completely different aisles. It's going to take a lot longer to get everything. The performance hit is just staggering. If the drive has to fetch just one more piece of that file from a different location, it has to do that entire mechanical journey, the seek, the wait, all over again. So a single bit of fragmentation can literally double your access time, just completely killing performance. So all of these physical bottlenecks, the seek time, the rotational delay, fragmentation, they were just screaming for a new solution, something that could get rid of the moving parts altogether. And this led to a completely new paradigm in storage. The answer was the solid-state drive, or SSD, and the difference is absolutely fundamental. An SSD has no spinning platters, no moving arm, no read-write heads. It just rips out that whole mechanical assembly and replaces it with silent, super-efficient flash memory chips. It's not mechanical, it's purely electronic. And the performance difference? Well, the numbers speak for themselves. An SSD can find data in 1/10 of a millisecond. An HDD takes anywhere from 4 to 10 milliseconds. That's not just a little faster, that's a 40 to 100-fold improvement just by getting rid of the moving parts. And your actual file transfer speeds are way faster too. So, with this kind of revolutionary speed, you have to ask, is there a catch? Well, as it turns out, the flash memory that makes all this magic happen has its own unique quirks. The main thing people talk about is something called memory wear. See, the tiny individual memory cells inside an SSD can only be written to a certain number of times before they start to degrade. To fight this, SSDs use a really clever trick called wear leveling, which basically spreads out all the write operations evenly across all the cells to make sure they all wear down at the same rate. But is this something you actually need to worry about? Let's run the numbers. For a really heavy user, someone writing 10 gigabytes of new data every single day to a modern 2 terabyte SSD,
it would take an estimated 82 years to hit the drive's write limit. Yeah, 82 years. So for the vast majority of us, let's be honest, memory wear is just not a practical concern.
Okay, so SSDs solved the speed problem. But there's another, more universal issue that affects every single storage device, whether it's mechanical or electronic. And that's the simple fact that they all eventually fail. This is probably the most important rule of data storage, period. Every drive will fail. It's not a question of if, but when. And that means a single drive is a single point of failure for all your data, which is why we need solutions at a system level. And the most common solution for that is a technology called RAID. It stands for Redundant Array of Independent Disks, which sounds complicated, but it's really just a smart way to use multiple drives together to do things a single drive can't, like go faster or protect you from failure. Let's look at the two most basic types. First up, you have RAID 0, which is also called striping. The idea here is to split your data and write it across two or more drives at the same time for a massive speed boost. But the trade-off is huge. There is zero redundancy. Zip. Nada. If one of those drives fails, you lose everything on all the drives. It's like a multi-lane highway. It's fast, but one crash on any lane shuts the whole thing down. Then you have the complete opposite, RAID 1, or mirroring. This is pure redundancy, all about safety. Everything you write to one drive gets instantly written to a second drive, creating a perfect real-time clone. If one drive dies, the other just keeps on working like nothing happened. No data loss. The only downside is cost, because you have to buy double the storage you actually get to use. Okay, so we've gone from physical holes in paper all the way to solid-state chips and these resilient drive arrays. So what's the big takeaway here? It's really that there isn't one single perfect solution. It's about having a set of different tools for different jobs. The key is to just use the right tool for the job. You know, those big, cheap hard drives, they're fantastic for archiving tons of data where speed isn't a big deal. SSDs are the absolute standard now for your operating system and apps, where that instant response is everything. And RAID gives you those system-level strategies to either chase performance with RAID 0 or guarantee safety for your critical data with RAID 1. Understanding this stuff lets us build faster and safer systems right now. But, you know, as our need for data storage just keeps growing exponentially, you have to wonder, what's the next great leap forward going to be? Thanks for watching.